Today we'll be looking at graphing sine and cosine functions. Now you graphed sine and cosine functions in functions and statistics. However, that's been a while since you've worked on those topics. So we need to do a quick review. So remember that if we're graphing y equals sine of theta, that if we think of the unit circle approach, that the y coordinate on the unit circle is going to be the sine of the angle, as opposed to the x coordinate on the unit circle will be the cosine of the angle. So I gave some angles here, 0, pi over 2, pi, 3 pi over 2, and 2 pi. I could continue to go on, and I could get some angles in between, but I'm going to use the unit circle to help me find these values for the sine of theta. So the y coordinate, so the sine of 0 is going to be 0. The sine of pi over 2 is going to be 1. Sine of pi is going to be 0. Sine of 3 pi over 2 is going to be negative 1. Sine of 2 pi will be back to 0. And then the cycle will continue on if I found 5 pi over 2, 3 pi, and so on. So if I sketch those points, let my horizontal axis be my theta axis, and my y-axis my vertical axis. I chose to scale my graph just to spread it out a little bit, so each of these little tick marks is a pi over 4, and I stretched the 1 all the way up to here, again just to stretch the graph out a little bit. And I graphed these 5 points and smoothed in a curve. So there was our sine of theta function. It has no phase shift, no amplitude change, and you should kind of remember hearing those terms in the past. A cosine function, on the other hand, I did the same type of analysis here, where I looked at an angle varying from 0 to 2 pi, going by pi over 2's, and wrote down what the x-coordinate was on the unit circle, and that was the cosine of the angle as I rotated around the unit circle. Scaled the graph similarly over here and plotted the points, plotted those 5 points, and I got this nice smooth curve. Now the graph does continue to the left of that 0 and to the right of this 2 pi, and we can actually see that the shape of this cosine function is basically the same as the sine function. It's just that they start in a different spot. The sine function will always start in a middle and then rise up as long as our lead coefficient is positive, and our cosine function will start at a high and go down unless we have, again, some type of a change as far as a notational change in notation of a number in front of the cosine function. Now, when you're in FS, you also graphed functions that had numbers that were lead coefficients or numbers that were in front of the angle. And so we need to review what those coefficients mean. So we have our general form here. For sine and cosine, the A, B, C, D in each case will have the same meaning. So the A, absolute value of A, will stand for the amplitude of the function. The B coefficient will be the number of cycles that you'll see every 2 pi radians. So in a 2 pi radian width, you'll see B cycles. So in our case, the cosine had just a 1 in front of this, so that's why we only see 1 cycle between 0 and 2 pi. Next, the C coefficient, that's our phase shift. And just like when we have, say, parabolas or absolute value functions, if C is a positive value here, this would actually be a shift to the right. And then D, remember, is our vertical shift. That's where the center of the graph will shift to, kind of the middle of the graph. Now, one more important concept is what the period is. The period is going to be the amount of time, or the length on my horizontal axis, that it takes to complete one cycle. And in our case, both the sine and cosine functions up above had a period of 2 pi. And in general, if the B coefficient is something different from 1, then we'd have to do a little calculation to determine what the period is. But it will always be 2 pi divided by the B coefficient will give us what the length of the period is, or the amount of, quote, time it takes to complete one cycle. So let's look at an example. So I have an equation of a sine function, and we want to determine a graph for this without a calculator, and I ask you to sketch the graph from 0 to 2 pi. Now the steps that you always want to start with on this is basically look at the ABCD and look at what each of those coefficients means. So we know that this absolute value of -2 is 2, and that's my amplitude. The period is controlled by B. So the period is 2 pi divided by 2, or pi. It will complete one cycle in pi radians. The pi over 2 is going to be my phase shift, and D, the vertical shift, is 5. And we'll get to the critical points in a minute. So remember, the first thing to start with is show on your graph where your vertical shift is. You kind of start backwards and we'll move the other way. So we use this 5 first, and I put a little dotted line along y equals 5, and that helps me remember that that's going to be the middle of my function. Then I kind of back up and look at my amplitude. My amplitude was 2, which means that the graph will go 2 units higher than 5, or the vertical shift, and 2 units lower than 5. So my graph actually is going to have a width this way of 4 units, but the amplitude is considered to be 2. 2 up from the middle, 2 down from the middle. Now we need to sketch some points, and we will start at our phase shift of pi over 2, but there's another concept that we need to talk about, and that's what a critical point is. And remember, on sine and cosine functions, they have critical points, which means places where the graph has highs, lows, and middles. And critical points will occur every 1/4 of the period. So this CP is standing for critical points, and every 1/4 of the period, something important will happen. So for instance, up here I have a little sketch of a general sine function without a phase shift, and my graph starts at a middle, or at a 0 in this case, and then it's going to end at 2 pi, and every 1/4 of the period it goes from a middle to a high, so there's an extra critical point, and then I move over another 1/4 of the wave and I'm to another middle. I move over a 1/4 of a wave, I'm to a low. I move over a 1/4 of a wave and I'm back to a middle. So we want to take the period divided by 4, or 1/4 of the period, and determine how far it will be from my first phase shift to get to my next critical point. And so 1/4 of the pi is this pi over 4. So when we graph our graph, we can see that we're graphing a sine function. A sine function will always start at a middle, but because this lead coefficient is negative, my sine function will actually go down rather than go up. And so my phase shift, I scaled my graph down here by pi over 4s. So I'm going to finish a cycle in 0 to pi, because the period is pi, but I want to graph all the way to 2 pi, so I've got my graph scaled so that it's going by pi over 4s here, so I have a convenient common denominator basically between my critical points and my phase shift. And so I go to the middle of the graph at the phase shift, which is pi over 2, which is 2 pi over 4. And because of it being a negative lead coefficient, I need to go down, and I need to know how far do I move to get to my next low. And my next low is going to occur a critical point later. So I add on pi over 4, and that will be my first low. Then I move pi over 4 again, another critical point, to get to my next value, which is going to be a middle at 5. And then I move over pi over 4 again to get to my next critical point, which will be a high. Move over pi over 4 more to get to a middle. Move over pi over 4 more to get to a low. Pi over 4 more to get back to a middle. Now that would have graphed this much of the wave. Now I have to graph all the way from 0 to 2 pi, which means I'm going to have to graph backwards, and I follow the trend. So I move back a critical point, back pi over 4 to get to a high, and back another pi over 4 to get to a middle. So there's the graph of my sine wave going from 0 to 2 pi. So sketch your vertical shift in first. Put in some little horizontal lines going amplitude up, amplitude down, and then you'll know to keep your graph within this region. Start at your phase shift, and then move according to your critical point measure to get to your next either high or low. Now, another thing we need to review is how do we find solutions to an equation like this if we want the y value to be 6. Now up above you can see that I sketched in here where it would be 6 on my graph, and I did a little sketch of a horizontal line to show where y equals 6. And I can see that there's a value that's quite close to 0. There's another value here that's quite close to my phase shift, or pi over 2, a little less than pi over 2. I can see another one here that's a little bigger than pi, one that's a little less than 3 pi over 2. And if I continued my graph off to the right, I know there would be many more places where my y-coordinate would be 6. So let's just review solving an equation like this. So if I want to solve this equation, we know our first step is to subtract 5 from both sides, or add -5 to both sides. Then I'd have to divide by -2. Now quite often when we do the algebra to this point, this ratio, the sine of this angle, has to equal -1/2. Quite often this is not something that we are familiar with as far as what this angle would be, that the sine of this whole big angle to be -1/2. And usually we'd have to use a calculator when we get to this stage. However, we don't need to in this case. We know what angle this whole hunk would have to be to have a ratio of -1/2. Drew a little unit circle, went down to -1/2, and I know that this angle and this angle would cause me to be different locations, different angles, different terminal side angles that would have the sine value being -1/2. So this reference angle in here is 30 degrees or pi over 6 radians. So there are a couple different ways I could name this angle. This one I would naturally call pi plus pi over 6 and say that this whole hunk of this angle, or that chunk, is equal to 7 pi over 6 plus 2 pi n. And then this angle, I have a couple different ways I could have named this. I chose this time to call it 11 pi over 6. So 2 pi less pi over 6, or 11 pi over 6. I could have also written this down as -pi over 6 plus 2 pi n. Then we would multiply both sides by 1/2, or divide by 2. And then finally I would add pi over 2. And I have the simplified version right here, getting a common denominator between these values. And remember, this has an n attached to it, so you can't add the pi over 2 to this term, only to this numerical part. And now I look back at my graph, and I can see that this first solution is a little bit bigger than pi. If I go back up here to my graph, here's pi, and I can see that this 13 pi over 12 is actually this location where I would have a point of 13 pi over 12 and 6 right here. And the 17 pi over 12 would actually be this solution. So I'm finding these two when I solve this, plus I know I can find more solutions by adding and subtracting pi from these two. So that's it for this video.